Chapter 1, we learned that when a positive charge is placed in a uniform electric field, the electric field and the electric force will point in the same direction, whereas when we place a negative charge in a uniform electric field, the electric field and the electric force will point at the opposite direction. In this chapter, if we place two charges stationary, positive or negative, in a magnetic field, it will not interact with the magnetic field. This is because when charge is stationary, V equals to 0. Therefore, according to this equation, when V equals to 0, our force will also be 0. Now, let's hear a fun song about right hand palm rule, shall we?
Right hand palm rules, right hand palm rules, right hand palm rules. It's your thumb, magnetic force, yeah. Your forefingers velocity, your palm, that's what I'm on, yeah. Your palm is your magnetic field,
A simple example on the application of right hand palm rule. Since your palm is your magnetic field, it will point into the page. Here, you can see your forefingers are following the direction of velocity. Since the charge observed is positive, then the direction of magnetic force will follow the direction of the thumb, which is upwards.
Now let's see the part of the uniform circular motion undergone by a charge moving in a uniform magnetic field. The moving charge will interact with magnetic field that causes it experience a magnetic force. And here is the formula. One thing that we need to take note is for positive Q, it will follow the direction of right hand palm rule, but for negative field, it will opposite the direction of right hand palm rule. As F is always perpendicular to the velocity, so we can predict that the speed will remain constant, only the direction of the velocity will change. Also, we need to note that the magnetic force always points toward the center of circular path. Therefore, the magnetic force will equal to the centripetal force. And here is the derivation of the formula.
From the equation R equals to mv over modulus qb, we can deduce that the greater the mass, the greater the velocity, the greater the r. We can also deduce that the greater the charge, the greater the magnetic field strength, and the smaller the radius.
Previously, we learned about one moving charge experiencing a force when it placed at magnetic field. Now, let's take a closer look in a current-carrying conductor.
In this conductor, many charges are moving together, creating an electric current. Since each moving charge experiences a force when in a magnetic field, the combined effect on all these charges results in a force acting on the entire conductor.
Here's how to use the right hand palm rule in a current carrying conductor. Since your palm is your magnetic field, it will point into the page. Here, you can see your forefingers are following the direction of current flow. Then the direction of magnetic force will follow the direction of the thumb, which is upwards.
So we all know in the previous part, on Mabel's part, we learned about how a magnetic force is experienced by an individual magnetic charge. So in this part, we're going to learn about how a magnetic force is experienced by a current carrying conductor. Just like the definition itself, the sum of magnetic force experienced by each individual of moving charge. Here, magnetic force is equals to magnetic force by each individual of moving charge times the number of moving charge itself. When the formula was rearranged again, the one that I've highlighted before will be the total number of charged particle, which is the capital Q. So we all know that I is equals to Q over T, thus I is equals to NQAV over T. Thank you.